Welcome to today's lecture. We just have started to discuss the response of fluid inclusions to microthermometric experiments to freezing and heating cycles. We discussed about the aqueous biphase inclusions, approximating them to be belonging to water plus NaCl composition. So, binary system of water and NaCl. However, we know that the crustal fluids, the natural fluid, are complex mixtures containing many more electrolyte species, and in reality we should possibly be considering such kind of multi component complex brines, but since the concentration of the other species would always be much less or negligible compared to some of the dominant chloride species like sodium chloride, calcium chloride and potassium chloride. So, it would be worthwhile to look at the ternary system, which is water, sodium chloride and calcium chloride, and from the phase relations at low temperature to understand what will happen to a fluid inclusion, aqueous fluid inclusion, which is an aqueous biphase inclusion like what we have been considering before. What will be the behavior to freezing cycle? So, here we see that this is a part of the ternary. This is the about 48% NaCl and also 48% CaCl2 like here. Now, on this ternary we are seeing the isotherms going up to, this is from minus 10, minus 15, minus 20 and so on, going to, this is the water rich region of the ternary. In this region it is beyond concentration of sodium chloride above this the correspond compared to the saturation value. So, here we will have the halite plus liquid, and as we know this small region will be having the stability of hydrohalite plus liquid. Now, what is going to happen, and kindly do recall that we had listed the values corresponding to ternary eutectics of some of the systems, and to recall the ternary eutectic in the system NaCl, CaCl2 and water is minus 52, around minus 52 degrees Celsius. So, if we have an inclusion which can be which is approximated, or it has calcium chloride also in addition to sodium chloride, then if we freeze it, decrease the temperature, then it is theoretically supposed to become completely frozen at minus 52, which we know is much lower than the binary eutectic of sodium chloride and water. So, you would expect the inclusion to remain in the liquid form till the temperature is lowered substantially to negative values, and also add the effect of supercooling to it, such kind of inclusion which become frozen at temperatures much lower, corresponding to sometimes minus 70, minus 80 or so degrees Celsius. So, now what exactly happens? Like before, suppose this star corresponds to the composition of the inclusion that we begin with. It is a water rich inclusion, contains sodium chloride which is less than 10 watt percent, and also contains calcium chloride, which will be of course will be even less than that. So, suppose we freeze this particular inclusion, then what is going to happen? We have supercooled it, and after the supercooling, when we are gradually warming the temperature, as and when the temperature of minus 52 is reached, it corresponds to this particular red point is corresponding to the sodium chloride, calcium chloride, water ternary. So, here this particular the inclusion, when we raise the temperature from anything like minus 80 or minus 70, when we slowly warm up, then we would expect to see the interstitial liquid like the way we explained in the previous case, the interstitial liquid to form at this particular temperature, which we will record as the ternary eutectic. Now, here it gives us a very first indication that the inclusion fluid that we are looking at is not a pure water NaCl fluid, but it also does contain other cations, and if it happens to be around minus 52, then we know that the dominant cation is calcium chloride. One important point also to mention here, that many of the situations we actually may not have the eutectic very well observable if the concentration of the other cations are much less, which is usually the case. So, that is why we are not considering the other sulfates or carbonates or bicarbonates system, but the fact is that they can be or they should be, but when we are attempting to approximate kind of a gross chemistry of the inclusion fluid, such kind of diagram suffice. So, here with increase in the, so from the Turner eutectic which is minus 52, we slowly warm up the inclusion and it follows this particular cotectic of hydrohalite and liquid, sorry hydrohalite and ice, because this is hydrohalite and liquid and this is ice and liquid. So, this particular cotectic is the cotectic of coexistence of ice and hydrohalite, whereas this one will be hydrohalite and halite. So, as it moves on this particular cotectic of hydrohalite and ice, as and when it reaches the temperature corresponding to this green circle. So, at this particular temperature the hydrohalite will melt out, because our bulk original composition is water rich. This hydrohalite will melt out and then it will enter into the ice plus liquid field, and on slowly warming the inclusion as we did before, it will go up these isotherms which are written as minus 20, minus 15 and minus 10, and suppose for example, say it is the last ice, solid ice melts about corresponding to minus 6 degrees Celsius. Now, the situation is that what we can do here, that we will again be calculating the weight percent NaCl equivalent as whatever we have been able to determine from the last ice melting temperature, and we will be expressing in terms of weight percent NaCl, and we expect that it is going to give us a gross value which could have been the which is essentially a cumulative effect of the depression of freezing point caused by this chloride species. Similarly, if the inclusion fluid, and in this case also it is a pure aqueous biphase, there was no solid phase. In this case also the bulk composition is slightly more sodium chloride compared to the first case, and here the freezing behavior will be such. So, this and also the point in the previous case, it will also give us a bit of an idea. If we extrapolate the point parallel to the axis of this H2CaCl2 binary, we will intersect the NaCl CaCl2 binary at a particular point, and that is going to give us the CaCl2 is to NaCl ratio in case of the inclusion, this particular first inclusion that we are discussing. If the inclusion liquid is more sodium chloride rich compared to the first case, so there the situation would also more or less similar to the case. It will have a ternary eutectic corresponding to the first melting will be observed corresponding to temperature of the ternary eutectic, and it will move on the hydrohalite plus ice cotectic, and at this particular point the ice will melt and it will enter into the hydrohalite plus liquid field, as has been shown in a magnified in a blown up this diagram has been enlarged here. This blue from this point which is indicated here with blue, with warming it will go across the isotherms, and we know that from the binary the temperature of melting of hydrohalite corresponding to the room temperature solubility of about up to 26.3 weight percent, it will be, it can go to from anywhere from minus 21.2 to plus 0.1, as we saw before in the previous case when we were considering the water NaCl binary. There the NaCl rich side, which will be from the eutectic composition to the room temperature saturation, the short curve which was joining the binary eutectic to the room temperature saturation value of sodium chloride, there the temperature can vary from the eutectic temperature of minus 21.2 to plus 0.1 degree Celsius. So, this is what will is likely to happen here once it enters into the hydrohalite plus liquid field, and finally, the hydrohalite will melt at this particular temperature, and we can calculate the weight percent NaCl equivalent by using the equation which we have discussed before. So, this is how. So, the practicality is that exactly remaining the same. So, whenever there are phase changes expected, because we generally do the replicate measurements, we get some idea exactly at what point, what temperature we are observing the phase changes, and as we are will be approaching those values of temperature, there we need to have a very controlled rate of warming the inclusion, so that this temperature could be recorded, and as I have said before, they have to be reproduced to limits of plus minus 0.1 degree Celsius in case of freezing experiments, and which is usually is achievable with the devices that we are using and the practice good practice of microthermometry that we can follow. So, as I said that in many of the cases, say for example, we do see some of the cases the binary eutectic or the first melting temperature. Sometimes they may not correspond to exactly the sharp value of minus 52 or minus. So, sometimes we find that if we have been able to confidently notice the temperature at which the interstitial liquid is forming, sometimes we find they do not exactly correspond to the known eutectic values. So, that possibly ascribed to one of the reasons is that the third component or whenever we are considering even a more complex brine, because of their concentration is so low that we generally miss out the actual eutectic value. And I think that could be whatever we can say about the freezing behavior, the melting of the solids or the eutectic temperature and the fast formation of the liquid, and we record them as temperature of fast melting corresponding to eutectic, and if we are able to measure the temperature of so for example, we can always denote the temperature of first melt as T Fm, temperature of first melting, and sometimes if we can very clearly notice in case of such kind of ternary, if we can very clearly notice the temperature of hydrohalite melting, we can denote it as THH, and temperature of last ice melting, which usually is represented as Tm, and this value is actually is the most important to us to calculate the salinity in terms of weight percent equivalent. If one can determine in case of a ternary sodium chloride, calcium chloride and water, if one can determine the temperature at which the hydrohalite melting, the extra information which can be obtained from the ternary could be the NaCl CaCl2 ratio. Okay. Right. So, now we could possibly, so that is in a very simple way we could illustrate, we could depict the response of aqueous inclusions, which are essentially water plus electrolyte, and their response to freezing, and with the basic objective that we want to approximate the gross chemistry of the inclusion fluid, and the best way that we could represent it in terms of weight percent NaCl equivalent. Because there are many other systems which are studied, but when it comes to the practical, and as we go to the advanced topics of knowing the chemistry of the inclusions, that we can do by many other microanalytical technique, but as far as the microthermometry is concerned, to constrain their bulk chemistry, gross chemistry and the thermal regime, we need to generate these sort of basic data. Now, let us try to look at that what exactly the response of this kind of aqueous biphase inclusions to heating. This diagram we have already discussed in the context of entrapment. So, the fluid was entrapped in the host crystal at a temperature and pressure corresponding to P 1 and T 1, and it has followed an isochoric path, and after intersecting the boiling curve, the vapor bubble nucleated, which also could be explained based on the differential coefficient of thermal expansion of the host solid and the liquid, and on further decreasing the temperature or further lowering of temperature and pressure corresponding to a situation where we are seeing them at room temperature is P 3 and T 3, we see the aqueous biphase inclusion in its typical liquid plus vapor state. Now, so it will be easier for us to understand that if we heat, what exactly is going to happen. So, exactly the reverse is expected, that was it is going to mimic the process of entrapment. So, if we increase the temperature, it is expected to move on the boiling curve, which corresponds to liquid vapor coexistence, and it will go on this particular curve till it reaches the point where the vapor bubble disappears, means it actually becomes homogeneous. It is being represented by the last dot that we are seeing here, and this will vanish and this will become a homogeneous cavity filled with liquid at this point. So, we note down or we designate this particular point at which we observe this as the temperature of homogenization, and we designate it as T h. Sometimes people call it THLV or liquid vapor homogenization, and which has been which is on the diagram you could see, which is shown by the red arrow. Here it is TH, the temperature of homogenization. So, now the thing is that if we further heat this particular inclusion, then it is supposed to be, or it will follow the isochore exactly the way it followed after its entrapment till the intersection with the boiling curve. So, the only problem here is that we have no way to actually come to this point of P 1 and T 1, because on this isochore, as long as even if we are going to heat, there will not be any further phase change, observable phase change, it will remain in its one phase state. So, how we are going to determine that will be the issue which will be discussed later, but then what one can say here is that if T 1 corresponds to the temperature of entrapment, means the formation condition of the host crystal and representing the geological environment in which our material of interest, whether it is a rock or it is an ore body that is formed. So, it formed at a temperature of T 1, and we also know that the processes never occur at any particular sharp temperature, it does take place in an interval, and this particular temperature corresponds to the entrapment of this particular single fluid inclusion, and it would have followed the isochore, and the condition of entrapment corresponds to T 1. So, what we have been able to achieve here is that we have approximated the temperature of the fluid, which was actually the temperature which is mentioned as T T as temperature of trapping, you can say temperature of trapping or temperature of entrapment, which is designated as T T. Okay. So, we know that by what value we have missed this particular temperature, because we have not been able to constrain from our homogenization experiment the value of temperature of entrapment. So, we are falling short by what is shown by this particular arrow. If we subtract T T minus T H, the temperature difference that we are getting is essentially called as a pressure correction, Why? It is known as pressure correction, because had we known the pressure of entrapment of this particular inclusion, then we would simply drop the perpendicular onto the temperature axis and we will be able to know the temperature of trapping. Again I will repeat that if there is some independent consideration, independent means of determination of pressure for the formation of this particular mineral in which this inclusion has been entrapped. Say for example, suppose it happens to be a sphalerite, in which I do a sphalerite geobiometry and I know that the sphalerite formed at that particular pressure, and I am analyzing the primary inclusion within that sphalerite, or for that matter any other host, or even if I somehow constrain the environment in which this particular process formed happened at a pressure of P1, then on this if I construct this isochore, and on this isochore if I know the value of P1, then I can drop the perpendicular on the temperature axis and can get the temperature of trapping. So, what essentially we are missing in this homogenization experiment is the value or we can say at we are approximating the temperature of trapping of the or the temperature of trapping or the temperature of the fluid by our temperature of homogenization, and we know that we are falling short by a few degrees. Exactly by what we do not know. That is the understanding for the time being. So, we have the pressure correction. So, that is the parameter which we call as pressure correction. Please remember, it is the term is pressure correction, but what actually we get is the difference in the temperature, means. So, this gives us by what degree we fall short of actually estimating the true temperature of the fluid. But eventually we will be able to do that, because we know that our data that we will be generating is will be the quantum of data will be more, we will be measuring inclusions hundreds in number. Well, this is a situation in which suppose the inclusion which was inclusion fluid which was trapped as shown here corresponding to P1 and T1 and had a density much less than the one which we just discussed. So, it is because of the density is less, it has followed an isochore whose dP by dt slope is much less compared to the previous inclusion. Let us say by virtue of the salinity, the previous inclusion which we considered has a salinity higher than the inclusion which we are considering here, and because the salinity will be low, even if they are entrapped at the same temperature, the density is less, and it will follow an isochore which will be the dP by dt slope will be much less compared to the previous one. So, here as you could see, we also do the same experiment of homogenization by heating the inclusion at 1 atmosphere condition in our system, and we will have the vapor bubble gradually shrinking in size till the point that vapor bubble will disappear, and we will achieve the homogenization that will be essentially we can represent as L plus V giving rise to L. So, it is a homogenization which is to the liquid phase, means the cavity will become entirely liquid from the original assemblage of liquid plus vapor. So, here then as you could see that if the situation is such that we are actually studying an inclusion which is much less dense, then the pressure correction is the magnitude of pressure correction is even more. So, denser is the inclusion, less will be the pressure correction and the vice versa. So, situation as we said that we always talk about homogeneous entrapment, and we also discussed that entrapment. So, this is the vapor stable field in a pure water system, or it can also be extrapolated to a water plus NaCl system where the topology remains the same, only with the change in the critical point and the exact position of the boiling point with respect to pure water. This is vapor, and let us say this P1 T1 corresponding to this star is the condition in which the vapor is entrapped in the cavity, a pure vapor, a homogeneous vapor. So, its density is vapor's density is very negligible, and we would expect it to follow a very shallow, a very less steep isochore, which dP by dt slope will be very low, but still it will follow an isochore and it will reach a point on the boiling curve, where what will happen exactly to the reverse to the situation which we discussed for liquid rich inclusion, that from this vapor a ream of liquid will form, because here is the situation corresponding to coexistence of liquid and vapor. Similarly, when we go down in temperature and pressure, the amount of liquid will increase, but still it will be observable as an inclusion where it will be liquid plus vapor inclusion, where it will be a vapor rich inclusion. Similarly, following the same procedure, if we heat this inclusion, what we expect here, that it will, the vapor bubble will start increasing in its size, will expand, go on expanding and expanding till the point is reached where the vapor will fully fill the cavity. So, here the homogenization will be in the mode of L plus V to V. So, in the previous case, when we had a L plus V to L, if we call it as liquid phase homogenization, in this case we will call it as a vapor phase homogenization. The only trick here is that it is very easy to record the disappearance vapor in a liquid rich inclusion, then it is to record a disappearance of liquid in a vapor rich inclusion, because the situation will be that, so we are here. So, that means exactly at the temperature of homogenization, the figure is a little exaggerated to show a prominent rim of liquid over here, but finally what exactly is going to happen, the vapor is going to completely fill the cavity. So, whether there is a very negligible very thin rim of liquid still remaining will be a situation which will be little difficult to determine. So, that is why we say that the uncertainty in the measurement of liquid plus vapor to vapor is little more. So, liquid this particular homogenization of liquid plus vapor to liquid is likely to involve a bit of an uncertainty compared to a situation where the homogenization is by disappearance of vapor, because the vapor I will just in this case I could just possibly discuss a little bit of practical situation as it happens in the aqueous biphase inclusions. Now, what happens is, you could possibly remember we were discussing something about something called as a pseudo Brownian movement. We all know Brownian movement, it happens in gas molecules. We know the kinetic theory, and we know that the molecules in a gas they undergo random movement, which is basically we know that is called the Brownian movement. Now, what happens in a aqueous inclusion, aqueous biphase inclusion, most of the cases, this particular bubble in most cases as it is observed, it undergoes some little movement, random movement, but not that very fast within the liquid region. So, this is actually represented as a pseudo Brownian movement. Now, what happens is that as and when the temperature is increased and the vapor bubble becomes smaller and smaller in its size, and just is so during that time the the amplitude, the movement, the pseudo Brownian movement become very vigorous, and the vapor bubble executes very random movement inside the liquid area in the inclusion cavity. So, that actually helps us in determining the liquid plus vapor to liquid, means liquid phase homogenization becomes far more easier to record, because just about when the time when the inclusion is tending towards homogenization, attaining of the homogeneous condition, the vapor bubble inside, which is reduced to just as a dark dot as has been shown here, exhibits very vigorous pseudo Brownian movement. So, then if we decrease the heating rate here, exactly we also will follow the same kind of principle, that in a first experiment we will crudely find that exactly at around what temperature the vapor bubble is actually disappearing. So, in the next time when we try to reproduce the value, we will decrease the heating rate to a very workable value, say 1 degrees per minute or even some kind of value, so that we would be able to see the focus on the vapor bubble and can monitor its presence or absence by virtue of the vigorous pseudo Brownian movement that it exhibits. So, many times many fluid inclusion workers report about this movement of pseudo Brownian movement in aqueous biphase inclusion, and they also take it into account for classifying them, but it is not a advisable thing to do, but to classify inclusions where the bubble is executing pseudo Brownian movement or not, because sometimes we observe that this pseudo Brownian movement is just because of a little bit of being thermally agitated, which can even be achieved by the light, the substrate condenser light that is coming and the light energy falling on the inclusion can also make the bubble move in a little random way, but the rate will be pretty slow. So, there are aqueous biphase inclusions which will exhibit variable degree of pseudo Brownian movement, almost static to very feeble, but as and when the homogenization is reached, the pseudo Brownian movement becomes very vigorous. And that also you would recall when I was saying that to which inclusion type to start with for our microthermometric experiments, and the pure carbonic inclusion whose temperature of homogenization can go up to a maximum of 31.1 degrees Celsius, and as we know, we are working in a room temperature where the temperature could be 24, 25 or 22 to 25 degrees Celsius. So, that means the inclusion will be very much close to its temperature of homogenization. So, the pseudo Brownian movement is sometimes rather more prominent or more vigorous in case of pure carbonic biphase inclusions. So, those are the ones which are very easy to identify and also to record the homogenization temperature in them, where the temperature only has to need to be increased to values of 30, 31, 32 or even sometimes much lower than that. Okay. Well, so this is the presentation that I have discussed here. So, it is the L plus V to L, and this is L plus V to V. And as I told that in this case the vapor bubble increases in its volume, goes on expanding till it fills the whole cavity like as shown here. It will be not impossible to measure, but it will involve a little bit of an uncertainty, which can always be bettered by this process. So, one of the very important practical aspect of doing the homogenization experiment is that how actually we more precisely record the temperature of homogenization in case of a liquid vapor inclusion. What we see on the forward direction, when we increase the temperature from room temperature to the homogenization temperature, the vapor bubble will disappear, and we have recorded that. Now, if we decrease the temperature from that point onwards, we expect that again the vapor bubble will nucleate there. But what exactly happens? The vapor bubble does not exactly nucleate at the temperature of homogenization, means if we start to decrease the temperature from the temperature of homogenization, it will not reappear instantly, but it would require cooling to some greater degree by 10, 20 or 30, sometimes even much more interval of lowering of the temperature, at which the vapor bubble it just pops up from any of the corner of this inclusion. So, that gives us the assurance that actually we reached the temperature of homogenization. So, we will continue discussing on the thermal response of the aqueous biphase inclusion in the next class. Thank you.